Hello guys. In our last class, we have studied how to design a ER model, and that is entity relationship model, which is used to describe our information world. And we have put these two exercise and homework. And before we give these answers of the exercise and homework, I will show you an example of how to design a ER model, and I hope this process can make you further understand how to design a ER model by yourself. And this example is give of how to design a ER diagram of warehouse management. And before we need to design the ER model, we need to make some requirements understanding. That is, what's the need of the warehouse management? So I have listed several. It's including the manage parts and manage the source of the parts. That is to say, which parts come from which suppliers, and we need to manage the whereabouts of the parts. And that is to say, that means which parts are supplied to which project. And we need to record which warehouse manages multiple parts. And we also need to record how to manage the employees. That means which employee manage which warehouse. So I have listed several these kind of requirements which we need to include the information in our ER model. So to design a ER model, the first step is to understand the requirements and find and confirm entities. So that is to say, if you want to understand requirements and find entities, the ER diagram modeling first need to find out the entities in the problem domain. That is to say, to find out which entities are there. So for these requirements I have listed here, we can see we need several entities. For example, we need parts, and we need suppliers as an entity, and we need here we need projects, and we need warehouse, and we also need the employee, and the employee is used to manage the warehouse. So here I have listed these 5 entities according to the requirements we have listed. And we need to make sure that we have covered every kind of things that can be managed independently involved in the requirements. So these 5 entities are the ones we need. And the second step is to describe each entity with attributes. So that's the second step. And at this step, we can see for each entity, I have listed several attributes. For example, for the suppliers, I have listed the supplier ID, a name, address, telephone number, and their account ID, which we need to transfer money to them. So for warehouse, we have warehouse ID, we have the area of the warehouse, and we have their telephone number. And for employee, we have the employee ID, we have name, their age, and title. For example, their projects, we have project ID, budget, and there's the start date of the project. And also for the parts, we have the parts ID, their name, and the unit price, and descriptions, and the specifications. So we need to make sure for each entity, we have at least give their important attributes which we need to record their information. So here I have put forward a question is, why are there no suppliers and warehouses in the parts entities? we can see I didn't put the suppliers and the warehouse as attributes in the part entities. So that is because we have used suppliers and warehouse as entities. So we don't need to put them as attributes of parts. So after we have confirmed the attributes of each entity, we need to determine the key of the entity. For example, for the suppliers, among these attributes, which one can set as a key? So here I set the supplier ID as a key. So we need to make sure that each entity, we must give a key in their attributes. That makes sure that the supplier ID is the key. So for the warehouse, we have the warehouse ID as its key. And for employee, we have employee ID as its key. So here, in this step, we need to make sure that each entity must mark their key. So in your homework of some students, I have seen that there are some students their ER diagram, they didn't mark the key of their entities. So after this step, that comes to the step 4. The focus of data modeling is to analyze the relationship between entities, and this is the most important step of our ER diagram modeling. That is the most important step. And here we can see that in this step, we need to model in the relationship between entities, between different entities. Here, for example, I use supply relationship as a relationship between these 3 entities, between the suppliers, projects, and parts. And that is because for the relationship supply, we need the information of all these 3 entities, not just 2 entities. We need all these 3 to make sure there is a relationship of supply. And here I also add an attribute of supply quality quantity as an attribute of the relationship supply. And here we need to notice that first, the relationship is built between or among entities. So in your homework, I have seen several students they didn't build a relationship between different entities. So if you want 2 entities or 3 entities or just several entities to have relationship, you need to build relationship between or among them. And for each relationship set, we can give their attribute, such as supply quantity. And if we put an attribute here, that means this attribute must related to all these entities this relationship related to. So I hope I hope I have this. So I hope I have explained this clearly. So then, for example, for the relationship between the warehouse and employee, I have put a work relationship here. And that means the employee works in a warehouse, and they need to manage this warehouse. And also, there is a relationship between the entity, parts, and warehouse. That is different parts is stocked in different warehouse. And also here, I put an attribute storage with this relationship stock. That means this storage is related with all these entities. So if the attribute is related to only one entities, you can just put the attribute here. But if the attribute is related to both entities, you need to put the attribute with this relationship. So after this step, we have analyzed all this relationship between or among different entities. And then we need to put this relationship coordinate here. So that's why we need to make sure that the relationship between entities are one-to-many, one-to-one, or many-to-many. So here, the relationship coordinate is also the one we need to write here in the ER model. So for example, for the relationship between warehouse and employee, we have one-to-many. That means for each warehouse, we have many employees, and for each employee, it always managed one warehouse. So it is a one-to-many relationship. And also, for the relationship between warehouse and parts, we have many-to-many relationship. That means for each warehouse, it can stock many kinds of parts. And for each part, it can store in different warehouse. So it's a many-to-many relationship. So it is very important. You need to write these numbers. You need to write this relationship to show that the relationship is one-to-one or one-to-many or many-to-many, and different coordinating may lead to different design schemas. So it is very important you put these characters in your ER models. And here we need to notice that many-to-many, we always put the character M and N that denotes the many-to-many relationship. And I saw in your homework some students write M and M. So it is not proper to write the same character in one relationship. But you can write M and M also in other relationship, not in the same relationship. You can't write M in one relationship. And also for this relationship between three entities, you can write M and P to represent this kind of relationship. And for the relationship of one-to-many, you can use 1 and N to represent it. So after we have write all these relationship, that is we comes to the final step, that is to check whether the relationship are covered, whether all these requirements we have write are covered. So we need to check this ER diagram if we have read the correct one according to the requirements we have read one by one. So first, we can see that for the requirements of managed parts, we have put the entities parts here, and we have the supply relationship, we have the stock relationship, so we can manage the parts. And for the second requirements of manage the source of parts. That means which part comes from which suppliers. We can do that too, because we have put entities suppliers here, and we have built the relationship. And for the third one, manage the whereabouts of parts, which part are supplied to which object. We can also make this. We can also satisfy these requirements too, because we have put an entities a property here. So for the last two requirements, we can satisfy them too. And I hope if you have time, you can just write your ER diagram according to these requirements you write, and try to do this kind of exercise of the ER diagram modeling. So it is contain the 5 steps. Okay, so before we introduce the context of this class, I will show you the answer of the exercise I have put last class. So in the last class, I have put these two exercises and I have leave a homework. And first, I will show you the answer of the homework, and then is the answer of these two exercises. Okay, so here is the homework we have lived in the last class, and then I will explain the answer of these two exercises. And first, we can see for the first one, here, the available information on classes, students, and courses is as follows. And here we have all these attributes describing different entities. And so we have these 3 entities, and we have the attribute for each entities. And the relationship is, suppose there are several students in each class. Each student can only belong to one class. Students can have multiple courses, and each course selected by each student has a record of achievement. That means we have a record score. And according to the semantics, draw their relationship model, the ER model. So here I have shown a correct answer provided by one of our students. And we can see here we have these 3 entities, is class, students, and course. And for each one, we can write all its attributes as the exercise mentioned here. For example, for the student, we have ID, name, gender, and age. Okay, so he write all these correct attributes. And for the relationship, we can see that each class it has many students, and for each student, he or she always belong to one class. So it is a one-to-many relationship. And for the relationship between student and course, we can see that it is a many to many it's a many to many relationship. And here it is not proper to write all these two M. It's better to use M and N to represent this many to many relationship. And it represents that for each course, it usually have many students. And for each student, it can select many courses. So it is a many-to-many relationship. So that is the answer of the first exercise. And then we can see the second one. Here, an entity side teacher and society. I added to the above question. And here, the society, I think the translation is not very proper. And here, the semantics way it means is the community, the community. So that means here it gives the attributes for these two entities. And so we just need to add these two entities, teacher and society, or you can use community as the attributes, as the entity. And lastly is the relationship. It says each course can be taught by multiple teachers, and each teacher can teach multiple courses. So that is a many-to-many relationship between the entity course and entity teacher, right? And then it says each student can join more than one society or one community, and the students enter the community in 1 year or in a specific year. So here means one student can join more than one community, and each community it can contains many students, more than one students, right? So it is also a many-to-many relationship. And here we have the attribute information of the year of the student joins the community. So here we can see the answer of our students. We can see two entities are added. It is teacher and community. And for the student and the community, we have a relationship join. Join. And here there exists attribute of the year, which year you join the community. This is the attribute for this this join relationship. And for the teacher, we have the teacher, the relationship between teacher and the course. It is a teaching relationship, and it is a many-to-many relationship. That is because one teacher can teach more than one course, and each course can be taught by more than one teacher. So it is a many-to-many relationship. And we can use the character M and N to represent this kind of relationship. And here I noticed that the relationship should be a many-to-many. So that is these two exercise. So here we can see for the two exercise we have lived in the last class is these two. And here I have shown the answer, the one of the answers, the one of the correct answers of these exercise 1, the first one. Let's see. It says you need to design a year model for the vehicle insurance company. So first you need to you need to analyze the requirements of the vehicle insurance company. So just remember the 5 steps of the ER diagram modeling, the 5 steps. Just remember these steps and make the analysis and the modeling according these steps. And it says the company has many consumers and each consumer has one or more cars, and each car can have one or any accident. So here I have give a proper one of the correct answers. Maybe your answer is not the same as mine, but if you can make this ER modeling proper, it can be right. So let's see the answer let's see my answer. Here I have analysis. There should exist 3 entities. Is person, or we can see is the customer, and we have the entity car, and we have the entity accident record. So for the for the customer, it should have these three attributes. It should have the driver ID, it should have address, and it should have a name. And if you put other related attribute here, it's okay. And for the entity of car, we have the attribute license, we have the model, and we have the information of year. And here you put other information related to the car, it's okay too. So for the relationship between customer and car, here it says each customer can have one or more cars, but each car only belongs to one customer, right? So it is a one-to-many relationship. Here we need to put a one and n here. And here the relationship, there shouldn't be direction. It shouldn't be. Here I made a mistake. It shouldn't be a direction. We just need a line. It's okay. So it's a one-to-many relationship. And here for the car and the accident, for the entity accident, we have the report, the accident report number, and we have the relation, and we have the date as its attribute. And for the step of 3, we need to confirm the key of each entity. So for the person, its key should be the driver ID, right? Because if you know a driver ID of a person or a customer, you can just you can just make sure he or she's information. So it is key. And for the entity of car, here I put the license. I put here as this attribute as a key, because it can determine the information of a car. And for the entity accident, I have put the report number as the key, because if you know the report number, then you can just make sure which accident here. So this is step 3. We need to mark this key in the ER modeling diagram. So for the step 4, we need to analyze this relationship, and I have analysis that it is a one-to-many relationship. And for the relationship between car and accident, we have the relationship of participate, and this relationship is one-to-many relationship. So it is means each car can have may have 0 or any or many accidents. So it is a one-to-many relationship, and we need to put 1 and n here to represent this kind of one-to-many relationship. So here I have put damage amount. That means how many we need to pay for this damage of this accident. So because this attribute is related to both entities, so I put this attribute here. So that is the analysis of the first one. And then let's see the second exercise. It says to design an ER model for the hospital, and the hospital has many patients and doctors. Related to each patient is a series of records of various examinations and tests. So here, I gave ER diagram, and we have the 3 entities. We have the patient entity, we have the doctor's entity, we have the log entity. And for each entity, we have these different attributes. For example, for the patients, we can have their patient's ID, their name, their insurance, and their date of admitted or date of checked out, and so on. And for the doctors, we have their doctor's ID, and we have their name and their specification, and so on as their attributes. And also for the entity of log, we have the test name about the log, and we have the date, the test date and time, and the test result related to this log. So we have these ones as their attributes. So after we have read all these attributes, we need to make sure we need to make sure the key of each attribute of each entity. For example, for the patients, we have their patient number here. The SS gene should be the key, and for the doctors, we have the DSS number should be the key of the doctors. And here for the entity of log, we have we can see that here there the it is not maybe for each attribute all these attributes are not proper to be a key. So that's why here I put log as just weak entities. Weak entities. What is a weak entities? First, the weak entities, it is no need to have a key for a weak entity. And for a weak entity, it means it is strongly dependent. It is strongly dependent to another strong entity. So for the entities we have introduced previously, it is all strong entities. Also, it is in contrast. For here, for the log, aside is as a weak entity. That means this log is strongly dependent to the entity of patients. So it means if we don't have the entity of patients, then the log entity is no longer exist too. So it is a weak entity. And for this kind of entity, we don't need to give a key. So that's why for the entity of log, we don't need to give a key for it. So here, the relationship between log and the patients, we have the history relationship. And here we can see I have added extra. We have added extra these two one as the relationship. So that means if you see this kind of thing, that means it is a relationship between weak entities and strong entities. So that is a ER diagram of the exercise 2. And here, as I have analysis, the answer I show here is now the answer is now totally correct, and you just need to revise according to what I analysis. So after we have talked about the answer, the design process of the ER model, let's introduce the context of this class. And in this class, we will introduce what is a data model. and we will learn how to design a data model. So what is a data model? A data model is specifics a unified description of patterns, including the data structures, operations, and constraints. So data model is the abstraction of the structure of pattern itself, and pattern is the abstraction of the structure form of data itself. So the database system, which we have introduced in the first class, the DBS, is based on some kinds of this data model. And it is based on this kind of data model to abstract, represent, and process data and information. And the conceptual model we have learned, the ER model is one of the conceptual model. It is an intermediate level from the real world to the information world. So as it is just a model abstract from the real world, it is independent of the DBMS. That means it is not related, it is not directly related to the computer world. And it is a model used for the database conceptual design, such as the ER model. And it is user oriented and the simulation of this real world. And it is the modeling of the information world. So it is a process of abstract from this real world to the information world, and we have obtained this conceptual model such as ER model. And the objects and the relationships in the ER model in this kind of conceptual model is reflecting the real world. And for the data model, we need to study in this course. It contains of these two parts. The first is the logical data model, which is always related with the DBMS. It reflects the overall logical structure of all the data. And another one is the physical data model, which is also related to DBMS and also related to the OS, operating system. So it is related to all these tools, and it reflects the structure of the data storage. So that means that it reflects how you store the data physically. And then let's see what elements in a data model. Here we have these three. We have the three elements. The first one is the data structure. So data structure means the data representation method. That means how you organize the data. So in this elements, the data representation method will determine the nature of the data and will determine the connection between the data. And the second element is the data operation, and it specifies the operations and operation rules that can be performed on data. So it includes the operators, the meanings, the rules, and the language, which we need the database language. Also, we call the circle language. To the implement operations and so on. And the last one is the data integrity constraints, which we need this to provide a means of definition and it can be automatically checked during operation. So for the element of data structure, we can see this is a description of system static characters of and type. And for the elements of data operation, we can see that it is a description of system geometric characteristics. So for example, let's see the relational model we have introduced in the last class. For the relation model, it is a kind of data model. And in the relation model, we can see all the schemas can be in the form of a abstract table. So for relational model, we can just see it is just a table, and each specific schema is a specific table with different column names. And what are the operations and constraints for data in the form of table is the context that we need to learn. For example, for this student information form, we can see it is model and it is a schema of a table which the student information form is the name of a table and the student number, the name and gender, the date of birth, and so on. These are the attributes of the table. And the char 8, the char 10, this kind of thing is the domain of each attributes. So we can see this is the schema of a detailed table. And this is the student transcript. This is also a table. It is also a schema of a detailed table. And then how to abstract these kind of similar schemas? We use relational model. So we need this relational model to abstract the schemas of different tables. So we need to learn the table, and we need to learn how to calculate the relation between different tables, and we need to learn how to use the constraints about tables. And here I have introduced these three classical data models, which including the first one is the relational model, and it is also widely used in recent years. And there are also another two models, and these two models, it is not widely used in recent years, but I also explain the data models here. And we can see that they have just different forms. And for the relational model, the form is table. And for this model, they use tree to organize the data. And for the March model, they use the graph to organize data. So first, I give an example of a relational model. That is relational model, and we can see it is a form of table. So here I have give a detailed table here, and we can see for the relational table, this detailed table is the data. Is the detailed data of the relational table, and based on this table, we can abstract a schema of this table, which is here. It is a student register form, and we have these attributes and their domain. So all the table name and the attributes domain, it composes the schema of the relational table. And for this kind of schema of relational table, we have another abstraction, that is that relational model. So the relational model is an abstraction of the schema, and the schema is an abstraction of the data. So from here, the relational model, we can see that it abstract the attributes here from based on these detailed attributes are abstract as the field 1, field 2, field 3. So it is two process of abstraction, and you need to know what's the difference between the relational model, the schema, and data. So next, I have given example of this model which informed of tree, and from the left figure we can see that this kind of model, it is composed of two elements. The first one is the entity tab. And we can see in a tree, each node is an entity tab. And between different entity tab, the age, also we call a relationship, it is a relationship. So for the age between different nodes, we use relationship to represent it. And we can see for this kind of model, the schema of this kind of model is here. And for each entity tab, we have the schema of these. We have different schemas. For example, for this entity tab A, we have this kind of schema which made up of the attributes of the department ID, the department name, and their address. And for a different entity tab B, we have different schemas according to this entity tab B. And the schema is made up of the attributes room ID and room name, and so on. And for this kind of schema, we have corresponding these detailed records, and we call the data. So this data are the detailed records according to the schema. And for example, for the schema of this entity tab A, the department ID, the department name and address is corresponding a detailed record in the data. So it's corresponding the D02 and computer, and the address is R1101. So that is the abstraction process. So we can see that the relationship between these detailed records or between the schemas, we use the direction. They have a direction to just point to another records to represent the relationship. And here I also give an example of the Marsh model, and we can see which is similar with the tree, with the model in the form of tree, but the difference is this kind of Marsh model, it is in form of graph, and the difference between tree and graph is that for a tree, for a father node, it can have many children node, and for a children node, it can only have one father node. But for the graph model, for each father node, it can have many children node, and for a children node, it can have it can have many father node too. So we can see it also represents these the node as a entity tab, and for each entity tab, it is an abstraction of the schema of these attributes. So for this schema of attributes, it is an abstraction of the detailed records. So the schema, for example, this the student ID, the student name, and grade, it is a schema of these detailed records as one. So we can see this relationship is also use this direction age to represent. So, and this kind of relationship is defined by users. So if the user he can't define one relationship, then this record cannot be found. So let's come to introduce the context of the relational data model, and it is also the important context of this chapter. And we can see that for the relational data model, it's just a table, right? And it is first proposed by the EF Code in 1970, and it is abstract from the table and its processing model. It is proposed by introducing set theory and logical theory on the base of the mathematically and strictly defining the traditional table and its operations. And it is also the three classical data models of database. And it is also the data model still used by most commercial database systems. And the standard database language, we also call circle language, is based on this relational model. And many theories in the database field is also based on this kind of relational model. It's based on these tables, a set of tables. And for the data structure and its basic concepts for this relational model, first for the data structure, let's see an example. And for this, based on this example, I give several concepts. For example, for this table, we have this table name as student, and we have each column. The first we have the first tuple of each column. We have this one as attributes, and we can also call the column or attribute. And for each tuple, for each record, we can call each tuple or each record, both okay. And for a detailed value in each column, we call it a component. And for this schema, made up of student and attributes name, and we have the student ID as the key. That means if you use the student ID as the key, you can just locate each record according to their student number. And for example, if we give these two relational model, we can see this is the table name, and is the table name, or we see it is the relational model name, and we have these attributes. And here we need to define the domain of each attribute. It is the range of the attribute values. For example, for the student number, we need to define the domain as year plus department number plus class number plus number. So that is the format of the student number. And for example, for the attribute of name, we need to set their domain as 5 Chinese characters. And also for the attribute of gender, we can just set the domain as male or female. And the other, that means if you set the domain, other attribute values which is not included in this domain is invalid. So then I can introduce the concepts of candidate key. It is also a very important concept in this chapter. So what is a candidate key? It means the value of an attribute group in a in a relationship which can uniquely identify a tuple. And if any attribute is removed from this attribute group, it will not have this property. And this kind of attribute set we call this candidate key. For example, for the relational model student and S number, S name, S age, and S class, S number is a candidate key because in this relationship, the S number of any two tuples must be different, and the attribute of S name, S age, and S class of two tuples may be the same. For example, we can have the same name and the same age or the same class of two tuples. So the S number is a candidate key. And then I gave another example, the course selection schema. And we have this S number, it means student number, the course number, and the S name, the C name, and the grade. Here we can make sure that student number and course number, they're together compose the candidate key, because we only need to know all the information of these two attributes. Then we can confirm that we can just uniquely identify a tuple. If we just know one information, we just know the information of one attribute, it can't identify a tuple. We need both two. And sometimes there are many groups of candidate key in the relationship. For example, for this kind of relational model, the attribute S number is a candidate key, and the attribute group S name and S address is also a candidate key, because two students with the same name and address, it doesn't exist, right? So these are two kinds of candidate key, and there are two groups of candidate key. And I also give another example: the employee, the employee and its attribute is here, and we can see for each employee it has a unique employee ID. But the mobile is also can be a candidate key, because if there is no exist of two employees have the same mobile phone number, then the mobile can be a candidate key. So the mobile and the employee ID, it is two groups of candidate key. And after the introduction of the candidate key, let's introduce the primary key. It means when there are multiple groups of candidate keys, we can just select one as the primary key. And the DBMS, as it used the primary key as the main thread, so it can manage the individual tuples in the relationship. For example, the attribute S number can be selected as the primary key of the student table, and the attribute group S name, S address can also be selected as the primary key of the student table, so we can just select one. And for the employee table, we can select the employee ID, or we can select the mobile number as the primary key. Here, we need to notice that we only need to select one candidate key as the primary key. And here, we also introduced the primary attribute and the non-primary attribute. So for the attributes contains in any of candidate key, it needs to called primary attributes. And in contrast, other attributes which is not in any candidate key are called non-primary attributes. For example, for the S number and the C number in the cross selection, these two attributes are primary attributes, while for the S name, C name, and grid, these are not the primary attributes. So at its simplest, the candidate key contains only one attribute. And as most extremely, all the attributes may be compose the candidate key. For example, this situation we call the OR key. For example, for the candidate key, teacher number and course number in the relational model teaching by teacher, this model, we can see it is only composed of, this model is only composed of these two attributes, and this two attribute is also the candidate key. So for this kind of situation, all these attributes compose the candidate key. So it is called OR key. And then let's introduce the concept of foreign key. It means if an attribute group in relational R is not a candidate key of R, but it corresponding to another candidate key of relation S, then this attribute is called foreign key of this relation R. For example, for the consumer number in the deal relationship, it is for the consumer number, it is not a candidate key in this deal relationship, but it is a foreign key because it corresponding to the candidate key in the consumer relationship in the consumer table. And two relationships and two tables are usually connected by the foreign key. So we can see the consumer number in this table is a foreign key because this consumer number is the primary key in this table. So another example for the student information for the student table, we have the student number as the primary key, and we have the department number as the foreign key because the department number is the primary key in the department table. And here, let's introduce these 6 properties of the relationship in the relationship schema. And that means if it is a schema, a build schema, it needs to obey these 6 properties. So here, let's see this one by one. The first one is each item in the table must be an individual basic data item. And second is the order of the attributes does not matter. And the third one is order between among tuples, it does matters too. And the columns must be homogeneous, and different columns can be must be from the same domain, can be from the same domain, and it is also okay from the different domain, and not two tuples can be exactly the same. So let's see these one by one. First, columns must be the homogeneous. That means the component in each column must be the same type of data from the same domain. And here I also give an example, a table. We can see that if for the age we set the domain is 19 to 20, or the domain is 1 to 20, then the birthday date here put here is not is invalid, and it's not proper. And for the gender, if we put the domain as a male and female, then the number 1 and 2 put here is not proper. And for the other, it's so on. It's the same. And for the second different columns can come from the same domain. For this kind of situation, each kind of which called an attribute, we must give different attribute names. Here, I also give an example. We can see that for these columns, it is from the same domain, and they also these are also a set of names. It is from the same domain, but for different columns, we must give them different attribute names. So if we give these columns the same name for the name and name, it is not proper. So for this kind, we can just revise the attribute name to the name two. And the third, there's no exist two tuples can be exactly the same. So for the table, the first tuple and the last tuple, it is exactly the same, and it is not proper. You need to revise or just delete this tuple. And then the order of the rows does not matter. That is, the order of the rows can be swapped, and this is called tuple disorder. That means these two tables, although the tuples is in different position, but it is exactly the same relation. And also, the order of the column does not matter. That is, the order of the columns can be exchanged. That means you can just exchange this column. And it is also known as the attribute disorder. So these are the same table. And the column we just need the attribute name to recognize it is which column. So it is not dependent on dependent on the order. The last one is all the attribute values must be atoms, and the attributes are not allowed to be a two-dimensional dimensional relationship. For example, for this kind of table, it is not a relational model because for this kind of attribute, it is divided into two attributes, so it is not allowed in table. And for this, it's the same because for this kind of records, it has two attribute values. So it means for the father of this name and for the mother of this name, they have two children. So it is not allowed if for each attribute values they have two values. It is not allowed. So this relationship we call it is the normalized relationship, and we can just change this kind of relationship to here to this kind of we can just delete the attribute children and just put the big children and the small children here. And for this kind of table, also we can just write their parents here. So it is a normalized relationship. And then we came to the operations, the relational data operation. Here I just introduce them, and we will learn how to use the data operations in the next chapter, and we use the circle language. So here I just put some sentence here. So for the operations, it includes, for example, the query operation, we use select, and for the storage operation, we use insert, delete, or update. And we will learn this very detailedly in the next chapter. And here is the last elements of the of the relational model is the integrity constraints. And the constraints means the conditions to which data must meet or must satisfy the relationship between data. So there are three types of the integrity constraints for relationships. It includes the entity integrity, it includes the referential integrity, and the user-defined integrity. So first, for the entity integrity, it means its definition is, formal definition is if an attribute A is a primary attribute of the relational schema R, then any tuples component on A cannot be none. So this is the definition of the master key or the primary key in the relational DBMS ensures the entity integrity. It means if for the attribute which is a primary key, its attribute value cannot be none. And for the second, for the referential integrity, here we can see its definition is an attribute. If an attribute A in the relational R is not the key of R, but is the key, but its physical meaning of the value corresponding to the key in the relation S, then A is called the foreign key of R, and A is in the values in R. Either take the values of K in S or take a non-value. That means, let's see the example. If for the student schema, S number is its primary key, and the department number is its foreign key, because the department number is the primary key of this department schema. So for this kind of thing, the number of department number in the information of the value of the department number in this student table its value must included in the department table of the must in the department must included in the values provided for the department attributes in the department table. So if here we only have 1 to 4, these 4 values. So here the file which is not included in this domain, this is not proper. So another choice is if the values you can't put these values include in this domain, you can just put a non value. This is right. And for the user-defined integrity, it is a constraint imposed on a specific relational database. And it always, we can define the uniqueness, unique of the attribute value. And that means whether it can take a non-value. And you can define the value range of the attribute. And you can define the restrictions on the value of different properties. For example, for this table, we can just put the restrictions on the values of different attributes. For example, for the last name, you can just restrict to the value to 5 Chinese characters. And for the sex, you can just restrict the value to the male or female. And for example, the age, you can just restrict the domain, the range in 12 to 35. So the DBMS it supports for all these integrities, all the 3 integrities we have just mentioned. and the entity integrity and referential integrity are automatically supported by the DBMS system. And for the user-defined constraints, the DBMS usually provides the following functions. First, it enables the users to define their own integrity constraints. And second, when an update operation occurs, the DBMS will automatically check the correctness of the update operation according to the integrity constraints which defined by the users. So it will check if the update is obeys the user-defined integrity constraints. So then let's come to the next part. It is how to design, how to transform the ER model to the relational model we have just learned. So we have just introduced that the process is from the real world, we need to abstract the information from the real world to the information world. And in this step, we obtain the ER model, and then we need to transform the ER model to the data model, the relational model, which used in a computer world. So here are the concepts and other concepts transformed from the real world to the information world and the information to the data world. So in the data world, we can obtain the records and the attributes. And here for the information world, which we obtain the ER model, we have the entities and entities attributes, and we have the relationship between entity size. And here, about how to transform the ER model to the table. We need to convert in the ER model to table design. And it is the foundation of the database design. And the primary keys in the database tables can uniquely identify the records in the entity size and the relation size in our ER model. And so based on this, ER model can be transformed into a set of tables in the database. And each entity size and the relation size can be transformed into the corresponding table. And here, I give an example. And this one is ER model which we introduced in the last class. And we can see to transform the ER model to a relational model, first we need to transfer the entities in the ER model to the tables. And for each entity, we can build a table for it. For example, for the entity goods, we can have a table of goods which including the attributes in the entity size. So we can just copy the goods number and goods name as also as the attribute of this table. And for the warehouse, it is the same. And for the warehouse entity, we created a table as warehouse. And for its attribute here, the warehouse number and arrow, we just put these two attributes as the attributes of this table. So for the relationship, for example, for the storage, we can just create a table for it. For example, here, we just created a table for the relation storage. And here we need to notice, as the relationship storage is a one-to-many relationship between the warehouse and goods. So for the attribute of the storage, we need to put the goods we need to put the number of goods, which is the key of the good, also as the key of the storage. And here we also need to put the key of the warehouse here as an attribute of storage, and its own attribute stock is also, we copied it here. And here we need to notice that for this one-to-many relationship, we need to set the many entities, the key of the many entities. For example, the number of the good as the key of the relation 2, the relationship 2. So for the many-to-many relationship, the management, we also created a table for it. And here, for the many-to-many relationship, we need to use both the key of these two entities. For example, the number of the employee and the number of the warehouse as the key of the relationship management. And here we can find that for the table of goods and storage, they have the same key. So we can convert these two tables into one table of good, and they use the they also use the number of goods as their key, and the attributes, we can put them together in one table. So here I have summarized the general rules and steps of transforming the ER model into relational model. So first, you need to first, each entity side is transformed in a relational table, and the key of the relationship is the key of the entity side. And the second, each one-to-many connection is represented by the key of the part 1 in the table, transformed by the part n. If the correction has attribute, it is also included in part n. And the key of the party n, the entity side, it should be the key of the relationship. And for the next step, the many-to-many connection must be represented by the introduction of a connection table, and the attribute consists the key of the connection side, the entity side, which is connected, and the attribute as the attribute of the connection. And here it is I need to delete it. It is now this page. And the last part is the representing specification as tables. So in the last class, we have introduced that there are two ways to convert the ER diagram, which containing a summary into a representation of a table. And here it is also the context, which is not the important context we need to learn. So you just saw it. You just saw it as knowledge. Just saw it is okay. For example, for the employee, which contain a job as manager, we can create it just two types of entity as two tables. And also we can just use one table to record these two information. Just merge these two tables is okay. So here I also put several popular data modeling tools, and here I have just put here. And this is the main context of this class. And if you have any problem about the ER design process or the transformation from the ER model to the relational table. You can, if you don't understand the exercise, you can just please feel free to contact me. Thank you. I give you the definition of the data integrity. The data integrity refers to the correctness and compatibility of the data. And we have the two solutions to prevent illegal data from entering the database. And in the application, the first one is in the application, we need to check. We need to add check code for each insert, update, and delete operation. And the second one is the database management system. They will use a certain control mechanism to check whether the stored data meets the specified conditions, and these conditions we call it integrity constraints. And we have the classification of data integrity constraints. It's about the column, it's about the tuple and the table, it's also about the constraints among multiple tables. So we have several kinds of data integrity constraints. And recall that we have discussed, we have introduced the integrity constraints of relational model. It is about these three. It's about the entity integrity, it's about the referential integrity, and we have the user-defined integrity. And let's see, for each integrity, we have several SQL implementation methods. For example, for entity integrity, we can add primary key. We call it primary key constraints, and we can add not non-unique when you created a table. And in this way, we can keep the entity integrity. We can keep this entity integrity, and we can see that the not non-unique it is a kind of unique constraints which can make the column the data in the column is not duplicate. And for the referential integrity, we can add foreign key constraints, and we can use the trigger constraints. And for user-defined integrity, we always use these check constraints and default constraints and trigger constraints. And we need to know that for the former two, the check constraints and the default constraints, these two are static constraints, and this trigger constraint we call it dynamic constraint. And first, let's see how to make this constraint implementation in SQL language. First is the data integrity and primary key. And we have introduced before that for the data integrity, if an attribute A is a primary attribute of a relation schema R, no tuple a complement in A can be empty. So the definition of this master code in the DBMS can ensure the entity integrity. And we know that for the primary attribute, we call it, it refers to the attributes that contained in any candidate key, and this kind of attribute, it should not be none. And for the implementation in SQL language, we can see that we can use the created table statement. And for example, we can add the keyword primary key directly after the column name. For example, let us see if you want to create a table employee. If you make sure that the ENO should be the primary key of this table, you can add a primary key just after the definition of this column. So it's about add a description to the end of the column definition of the create table statement. And if for the case that the primary key is made of multiple attributes, then you can use another writing solution. You can use the primary key writing here at the end of the definition, and you can use the multiple attributes just inside here, one by one. So these are the two types of the definition using primary key to ensure the entity integrity. And there is also a solution that if you don't want to create a primary key during the created table process, then you can use this alter table statement. So you should write the alter table name and then add primary key and to this specific column. So you write column name list here. And for example, if we want to add a primary key ENO, these two attributes as the primary key to the item employee table, we can use this SQL language alter table item employee add primary key ENO. And here we need to know what's the difference between the unique constraint and the primary key constraints in terms of their foundation and definition methods and how to do the unique constraints related to the primary key. And first, we need to know for each table, we have several types of candidate key, and each attribute belongs to any candidate key. It should not have tuples to be duplicated. So for each attribute belong to any candidate key, you should give them unique. But for each table, we have only one group of primary key. So that's the difference. That is for a table, we can have many types, many groups of unique constraint, but we only have one primary key constraint. And if you want to, and for the candidate keys, you can use unique and not none to constrain them. And for the unique, it allows not line. It allows empty. But for the primary key, it don't allows empty. It should be not none. And second, for the relational integrity and foreign key, we can see that. So for these four situations, we have talked about that if for a parents table where it's a references relationship, for example, for the employee table, we have the DNO, and that is department number. This attribute, it is a primary key of this table. So it should reference the DNO attribute of the department table. So for this kind of referential relationship, we have these four conditions that is not suitable for update. For example, for the first one, if we want to insert a record in employee whose DNO value is not none, but does not appear in the department, table. So this is not correct, right? And for these three conditions, it is also this kind of thing. The second one modifies the employee's record with the new DNO's value, which is not none, but it is also not appear in the department table. So it is also not correct. So for these four situations, in order to deal with them, we have this, we will need to set this referential integrator between the two tables. So it's between the parent table and the subtable. And the attribute or a tuple F of the table R refers to the attribute A of the table P. So we write like this. A is P's primary key. So the value of the RF should be, or you can be equal to the medium value of the PA, or you need to take a non-value. So we can write this kind of reference integrity to keep these four these four conditions do not appear. So for the SQL language, we can define this kind of reference constraints like this. For the atom employee table, if you want to define this referential integrity during the process of creating the table, you can write like this. First, you need to define a table and the table name and the table's attribute, and we set the UNO and INO as the primary key. And as the UNO and INO is also the foreign key of the employee table and item table. So we write this foreign key UNO references employee UNO and foreign key INO reference INO items INO. So this is the usage of the SQL language of the referential integrity. And to implement the strategy for the referential integrity constraints, we have these three types. First is the restraint. It is the default strategy for the SQL language, which is suitable for the above four situations. And we have the cascade option, which is suitable for the later two situations. And also we have the not none, which is suitable for the later two situations. And for the later, these two, they have the difference is that for the cascade, if you write this kind of option, it will make these two records not appear. And if you want to delete or modify the record in this table, then the corresponding value in this employee table will be updated, will be deleted or modified the same as the value in the department table, which is we call the cascade. And for the set none is that if the parents table, the primary key column in the parents table, it needs to be deleted or modified for our employee table, their attribute value should be, we will set it as none. So it is not keep the same as the updates. So these two options are not the same. And for these three strategies, we have on delete, on updates, these two. You can choose. And here we need to know that for the Oracle by HI, it only supports cascade to have To have undelayed expect for restraint. And for the circle survey 200, it supports the updates and delete cascade. And here I also give several examples. And we can see the first one is, or we talk about, we can add this two foreign key to reference different tables, and we can write on delete cascade to make this option clear. Here we use cascade means that if the values in this parents table, this employee table, the ENO is updated, the ENO in our atom employee table should also be updated. And we write on delete cascade means the values in ENO if it is deleted, so the value in the ENO of our table atom employee should be deleted too. And for the foreign key, INO references items INO, it is the same thing. And we can also use alter table to add this kind of foreign key here. We can use alter table employee, add foreign key DNO references department DNO. And here we can write on delete cascade, which is the same with this one. And we can write on update set none. And this means that if the value of DNO in department is updated, then the corresponding value in our employee table, this DNO, is set to none. And here there is a question, can the foreign key be set to set none here? And here we can see that here we can write the foreign key, we can set to none, but here we can't set this foreign key DNO to none because here we have this update set none option. And the third one is the user-defined integrity and default and check. And here we should first describe what is a user-defined integrity. And it is also depends on the needs of application environment, and is semantically related. And we also use several methods such as not none, default, check, trigger, and accession, and so on. And here we just introduce the check and trigger, these two solutions. And for the first one is the check constraints, and how to use these check constraints to be a user-defined integrity constraint. First of all is check constraints. These constraints can be any clause that appears in where. So therefore, it